The All-on-4 treatment concept was first performed in 1998 by Professor Paulo Malo. All-on-4 means that all teeth are supported on 4 dental implants. Patients treated with All-on-4 often suffer from edentalism or occlusal loss. All-on-4 not only has high stability but also reduces foreign body sensation. The All-on-4 includes 4 implants, 2 anterior vertical implants and 2 posterior angulated implants, which can support an entire dental bridge on a jaw. The All-on-4 implants are designed for immediate loading. Finite element analysis has been used to study the biomechanical response of the jawbone with various implant designs and placements for All-on-4 treatment. Due to the complex geometry, contact, and boundary conditions, a single simulation can take a significant amount of time. For design optimization, many simulations would be needed and it can take days to obtain the results, making it difficult to use simulations in a clinical setting for real-time decision support. The machine learning techniques can be used to build a fast surrogate of finite element analysis for accurate estimation of biomechanical responses. The techniques have been used to predict breast tissue deformation, bone load, and stress distribution. In this video, we demonstrate a design workflow called ANN-PSO, which integrates the ANN into the particle swarm optimization technique to enable real-time optimization for All-on-4 implant design. An ANN that learns from sophisticated finite element analysis data was trained to act as a biomechanical solver for evaluating the objective function by a set of given input parameters. The aim is to develop a system to provide real-time decision support for personalized All-on-4 implant treatment. The right-hand side of the flowchart shows the training process. First, we program a Python script to run finite element simulations and collect data for training the ANN. The script automatically creates FEA models in Abacus according to input implant design parameters and the geometry model of the jawbone. To complete the training, the loss function was calculated during training to minimize the error until convergence was reached. The main ANN-PSO optimization workflow for All-on-4 implant design is shown on the left-hand side, which implements a PSO algorithm combined with the ANN-based biomechanical solver. A population of initial designs iteratively evolves to an optimal solution by reducing the mechanical stresses in the peri-implant bone regions. The input parameters of our ANN model include the length, diameter, position and tilt angle of a distal implant and the position of a mesial implant. This results in 10 input parameters in total. An additional input is the type of jawbone, for which we define 4 common types of shape. 700 design points are generated for each type of jawbone, resulting in a total of 2,800 design points for the whole dataset. The dataset is split into 90% of the training data and 10% of the test data. The output parameter is the mean stress in the region surrounding the 4 implants. The training process is shown on the left-hand side. The MSE is calculated and used to determine whether convergence is reached. We also apply techniques and adjust the hyperparameters to avoid overfitting. The final training result was satisfactory, with an MSE of 1.988 *10 to the power of -5 and a correlation coefficient of 0.9948, indicating that the training was successful. The ANN-PSO could reach an optimal design in seconds, given an input jawbone. In the case of RH jawbone model, for example, the average stress in the peri-implant bone area was reduced from 8.08 MPa to 4.58 MPa after optimization, showing an improvement of 43.2%. The prediction accuracy of the ANN-PSO was verified for the optimal designs obtained in all cases, which showed an average error of 10.4%. This demonstrated that the ANN-PSO could help quickly explore a much better design with high computational accuracy. Next, we perform shape optimization for the All-on-4 framework based on the optimal implant design. The goal is to maximize the structure's stiffness by a given volume fraction to reduce the usage of hard material. The bidirectional evolutionary structural optimization algorithm is used to perform the task in a predefined design region. The decision to replace a material element or not is based on the sensitivity of the element when subjected to force. This process is repeated until the convergence criteria are met. The final design will have the same volume as the initial ones, only the volume ratio of the hard material to the whole will be reduced to a given value. The animation shows the evolution of the shape optimization using Besso, and the corresponding results by iterations are on the right-hand side. The compliance rapidly decreases in the first 10 iterations, slows down, and converges to 258.39 nm, from the initial compliance of 313.86 nm. We finally replaced about 73% of hard material with soft material and still improved the stiffness of the framework by 18% of compliance. Finally, the optimized shape of the framework is exported and processed through several procedures, including smoothing, surface patching, and so on, to complete the final framework design.